Hello, in this video I'm gonna be explaining this TSM counter program from Max 10 from Intel. So we are using the Quartus Prime Little Edition program. So first of all, sorry, wait me for a second. Well, this provided VHDL code outlines the implementation of a fine state machine, or in short FSM, counter on the Max 10 Fpga. So first of all, we have the entity declaration of this FSM counter. This part of the code is the declaration of the inputs and outputs of the FSM counter. This includes the clock signal of 50 MHz, the reset signal, and the addition input for reset. Now, also includes the outputs of the signals of the clock, and also the LED count and the segment anode. Now we have this part of the code that is the architecture section, and this is the state machine. So this section describes the behavior of the FSM counter. It starts with a clock divider process that generates a slower clock from the input clock of the 50 MHz to synchronize the FSM operation. Now we have the clock divider. This process generates a slower clock by counting clock cycles to the input clock. So it will also be of 50 MHz. It resets the clock counter when the reset signal is asserted and increments the counter on each rising edge of the input clock. Now we have also the slower clock is then assignment to the output port of clock out, as you can see. Now, as you can see, we have 23 in this part. So this will be the velocity of this clock. So if we put something around 25, it will be slower. But if we put something around 1, it will be faster. So I use 23. When we jump to the physical part, you will see the LEDs and how it's moving around. Now, let's jump to the clock divider section. Well, sorry, we have already explained that. Now we have to explain this part. This is the conventional process. So the conventional process, this process defines the state of the transitions of the outputs of the FSM counter based on the present state. It utilizes a case statement to specify the behavior of each state. So as you can see, we have these cases. From 0, it will be displaying 0 in the LED count and also in the segment. So this is a 0 in a segment. So when it's like a state machine, and it will be changing the process when it finished the first state, the second state, the third state, the fourth state, the fifth state, and so on and so forth until we get to the 0. So it will be from 1 to 9 and then jump to 0 and then 1, 2, 3 and so on. So also we're using this part of code that says seg anode, not seg. So if we are using anode, but if you're using a cathode, you will need to replace this part of the code, and so we're using this part of code because if we use a cathode in our protoboard, it will be displaying the numbers as usual. So keep it in mind. Now this is the VHT code. So we are using this to see how the program will work in a simulation. So As you can see, we have this code. This is auto-generated by Quartus Prime. It's a model sim Altera VHDL. So the code begins in this part where it says list connection. No, sorry, this part of here that it says code executes for every event on sensitivity list. So this will be the main loop of the code. So this block of VHDL code serves as a clock generator process for signal name clock 50 MHz. Within the beginning and end of the block, there's a loop labeled as clock loop, indicating repetitive sequence of instructions. So this loop iterates indefinitely, continuously, and generating clock pulses according to the specified timing. So with each iteration of the loop, the clock signal 50 MHz is first set to 0, as you can see, representing a falling edge. This transition marks the start of the new clock cycle. Well, following this assignment, the process halts to execution for 10 nanoseconds using a wait for statement. So it will have a 0 and it will wait for 10 nanoseconds. So this delays the simulation during the low phase of the clock signal. Now, subsequently, the clock signal is set to 1. So this is indicating a rising edge, which signifies the end of the low phase and the beginning of the high phase of the clock cycle. So as you can see, there is another wait for the statement is used to introduce a delay of 10 nanoseconds, representing the duration of the high phase of the clock signal. So the loop will continue its execution, repeating the process to generate a subsequent clock pulse. As there are no exit conditions specified within the loop, it iterates indefinitely, continuously producing a square wave clock signal with a period of 20 nanoseconds between the low and the high. So as you can see, 10 nanoseconds for the low, 10 nanoseconds for the high. So this clock generate process is crucial in digital circuit design and simulation, as it provides a stable and consistent clock signal necessary for synchronizing operations within the circuit in FPGA and ASCII designs. So we are using FPGA if you haven't already noticed. And now let's jump to the physical part.
Hello, now we are in the physical part. As you can see, this is a loop. It starts from 0 and will go from 0 to 9 and then we'll jump to 0. So it's a loop. And first of all, we have this switch. This will reset the loop. So if I press this up, it will reset. So the reset is set to 0 as the first state of the machine of states. So it's in 0, as you can see. And then it will start again if I pull this down. And also we have this stop. If I pull this up, it will stop within the loop. So if it's in 1, for example, it will stop in 1 and so on. So check this out. I stop it right in the 9. So what happens if I pull up the reset and also I have this stop in 9? So it will reset to 0, as you can see. And if I put the reset down, it will stay in 0 because it's stop with this switch that is the stop. So if I pull down the stop, it will continue. So I hope you learned something from this video and see you in the next one.